Right, so getting more into it now with magnetic flux and flux linkage. Now, this whole topic, which again I think is very critical, because this is a topic that explains how we generate EMF or electricity. So this equation here, which doesn't come up until the next bit, this is kind of Faraday's law, Lenz's law, a bit in there. Faraday's law that the EMF produced is equal to the number of turns times the flux divided by the rate of change of time. Or the EMF is the rate of change of flux linkage, right? So that's kind of n phi per second. So that's just the number of turns. So the amount of flux per second is the EMF produced. And this kind of all builds up to that. And obviously then the thing about how we make electric current is we do it by rotating a coil of wire in a magnetic field. So if I show you my crudely created model, the idea is that whenever my coil of wire cuts through these magnetic field lines, now my coil of wire can't cut through these because these are physical lines. The reality is that magnetic field lines are not physical things. You can't see them, and wire can cut through them really easily. And every time the wire cuts through them, that creates a potential difference, which causes a current to flow if it's in a complete loop, or as in it creates an EMF. So if I kind of just show you an example, if I have my loop here and I move it like this, it's not cutting through anything. Yeah, I can do that. Anything I can do with this model is not going to make electricity, right? If, however, I try and go through here, my loop's going to cut through. If I were to show you what happens when we make electricity, which is we rotate this loop in the coil of wire. So we rotate it like that in the coil of wire, use sort of turbines and generators and all that sort of stuff to rotate this. That's what makes electricity, because it's literally cutting through these field lines. And you know, the thinking on this has changed a bit. When I did A levels, it was kind of very much, I was of the mind that when the wire cuts through this per second, the rate at which that happens, the flux cutting, but the kind of wording has changed and it's moved away less from flux cutting because these field lines don't really exist, right? But you can see that when my wire would ever cut through something like this, that's when you get electricity produced. And this whole topic just builds up to the maths of that and of that particular equation. But it is difficult to visualize again. So I'm going to try and use my little wire when I can. Difficult to visualize because we've got this whole like 2D diagrams and we're trying to figure out what's happening in 3D. Now, the first thing is there's some terms to talk about. So this is our big equation that we're leading to, because this is like how we're making electricity, which is how I'm filming this, which is how you're watching this. So it's pretty important. It's a pretty big deal. We have magnetic flux density, which we already met. I think previously I called it magnetic field strength, which is, it's the same thing. The flux density is what we consider to be the field strength. We then have something called magnetic flux. Now, if you think of the density as sort of like the number of field lines per meter squared or something like that, then the magnetic flux is actually how many field lines you cut through. So how many field lines has my little coil of wire actually cut through would be the magnetic flux, and that's measured in Webers. We have the area because they're all linked together, and then we have the number of turns, because this is a 2-turn coil, but obviously if I had more turns, each bit of there would be more kind of cutting happening. And then this thing called flux linkage, which is also measured in Webers, because number of turns doesn't really have a unit, but sometimes it's called Weber turns as well. Now, magnetic flux, how many field lines you've cut through, is equal to the magnetic field strength. So phi is equal to the magnetic field strength, or the magnetic flux density, times the area. They have to be normal to each other or perpendicular to each other, right? So if I had just a straight wire like this and I cut through those field lines there, my magnetic field strength here, and then this is the area I've cut through, right? So my wire has cut through that the area that I've cut through will give there, and then I can work out then how many how much flux I've actually cut through, which will then lead on to tell me how much electricity I've produced as the rate at which I've cut through those flux lines. Now, obviously though, quite often, instead of just one wire, you have like 2 loops of wire, right? So the number of turns is important, because if I do this, I've doubled the amount I've cut through, And this is then called flux linkage. But again, it's kind of silly because all I really do is I just do n phi to tell me the flux linkage, and then was a number of terms times the magnetic flux density times the area. So n phi is n NBA. It's a kind of slightly strange equation, but that is what tells me how much flux linkage I have, right? So how many times have I made this flux, which is then important because this is the little bit that's going to go into making how much EMF I've produced, right? The number of terms times the flux. Now, the next bit is a flux linkage, flux and fluxation point through a rectangular coil rotated in a magnetic field. So if I make a single kind of rectangular coil out of my little bit of, I think it's wire, my little bit of wire, right? We can get an idea that if I rotate this in this magnetic field, right, we're going to cut through field lines and therefore we're going to get an EMF produced. Now, when I have it actually like this, right? Oh, I need to make it a bit smaller. I'm just going to do a circle. It's the same for a circle, but it's just a bit easier shape to make. So when I have it like this, yeah, kind of like parallel, actually I'm not making much flux, because if I show you this model here, when I have it like this, actually I'm not really cutting through much. When I have it like this, that's when I'm going to be cutting through the most. So we use cos for this. And what we say is that the angle theta here is the angle from the normal of my coil of wire. So as in at this point, cos theta is 90, right? Here they're perpendicular. So the angle between the magnetic field and the normal, do you remember the normal? That was the line from when we do kind of refraction, yeah? So the normal is a line at 90 degrees to the surface. So when we have it like this, the angle between the magnetic field and the normal of my coil is 0, because the normal of the coil is where my finger's pointing, it's the same, right? So we use cos for this. So theta is 0, cos theta is 1, so n phi is BAN. If it's like this, it's 90 degrees, right? Because the normal of my coil is now down into the page or coming up like that. And my finger, pointing up, and the field is at 90 degrees. So we say theta is 90, so cos of theta is 0, so n phi is 0. Right? So no EMF is produced then, max EMF is produced then. And then you get this equation here, n phi is BAN cos theta. So if the coil is rotating, right, the EMF produced, or this is just the flux produced though, but you can see we go from flux linkage to EMF in the next bit. It's going to be, assuming it starts with theta is 0. So if it starts like this, it's going to look like this. Yeah? And theta is the line perpendicular to normal. So you're going to get the EMF produced, or the flux linkage there, which is going to be shortly the EMF produced, because that's the whole big deal of this, is going to be related to the cos function, right? Then there's the equation. There's a required practical after this, which is the search coil one, where you investigate the effect of magnetic flux linkage on the search coil between a magnetic field direction. So you put the search coil into a coil of wire which will have a magnetic field acting on it, and then you kind of move it around. I think it's a slightly misplaced practical, but it's just my opinion. Right, so the next one then is going to look at that EMF equation there.